Hello, welcome to the week 7 of this tutorial sessions. And my name is Sharmi, and I'm a research scholar at the Department of Mathematics, IIT Delhi. I welcome you all to this session. And in this week, you guys have studied about this compact embeddings of the Sobolev spaces into the big spaces, LP spaces, and you see that as we increase our P, we see these Sobolev spaces are turns out to be more piece somehow more greater than we have a more better embedding, in fact, more better embedding to the continuous functions. And after that, when we define the Sobolev space any integer m, we try to generalize the Sobolev spaces for any real number s. So we define the Sobolev spaces WSP for any s real. So for negative, we realize it can be seen as a dual space of our this W naught 1p space, W naught MP spaces. And after that, we uh, define the fractional Sobolev spaces. Uh, those fractional Sobolev spaces are actually can be defined in various ways, but if you're considering functions to be very smooth or CC infinity or like something like that, then various definitions actually coincides. And moreover, um, after that, we have studied that about the value of this Sobolev functions on the boundary having measure zero, it function may not make sense there, but we try to make sense of that with help of this trace embeddings or trace functions or trace operators. And these trace operators are helpful in defining what do we mean by like the notion of the Sobolev functions on the boundary. So we just started that. So for this week, we will do questions based on these compact embeddings mostly, and something with the this characterization of this fractional Sobolev spaces. When we have this p equals to 2, so it forms a Hilbert space, and we use the Fourier transformation to basically define the fractional Sobolev space. So mostly we will see questions or problems based on these two concepts. So without further ado, let us start our session. The first question is that if we have a like we use the Fourier transform to prove that if U belongs to HS Rn for s greater than n by 2, then U belongs to L infinity of Rn with the bound at the L infinity norm of Rn has to less than equal to some constant time the HS norm of Rn. And that holds for a constant depending only on S and N. So we need to prove this. So it's says that essentially after a stage, like we have seen that when as uh, for a compact embedding, we have this sort of type of inequality, but we are like uh, we can prove this with help of the Fourier transformation to have this sort of inequality when essentially after the stage, if I take S to be greater than n by 2, my function is smooth enough. So as I increase my s, the Sobolev functions tend to be more smoother. And we have seen in the video lectures when my s tends towards the negative infinity, we see that even Dirac delta functions are actually belonging to these spaces. So the Dirac delta being very discontinuous, it's like a laws of heavy differentiability. These type of functions are trying turns out to be belonging to the Sobolev spaces as we tend ours to minus infinity. So let's prove the question. So to prove this, first of all, we prove the CC infinity function. So let U belongs to D of Rn, which is a subset of Scott function. Then what I know that Ux can be written as integration of Rn of E 2 pi I by the Fourier inverse transformation formula 2 pi I x dot xi into U hat xi d xi. So it's by the Fourier inversion formula. So what we can now write, so also we call that HSRN is actually defined as all those U in L2 Rn such that 1 plus mod xi square s by 2 U hat belongs to L2 of Rn. So this is our actually characterization of this Sobolev function with help of the Fourier transformation. So we will use this vector characterization. Then mod ux is less than equal to integration of Rn mod of U hat psi dz, and this is further can be written as integration of Rn U hat psi 1 plus mod xi square s by 2 1 plus mod xi square minus s by 2 dz. Is whole further less than equal to, and then here we can use the Cauchy's cos. This integration of Rn U hat psi 1 plus mod psi square s by 2 whole square dz half, and then integration of Rn 1 plus mod xi square minus s dz half. This is nothing but the norm of u in the HSRn, and this is all multiplied by Rn. So this is the we have this. So this thing is more or less what we want, but all we need to show that the right hand integral has to be finite. So to show that, so let us consider the integration of Rn 1 plus mod xi square is power minus s d psi. This actually by polar coordinates Let me write this first cautious pause. This can be written as omega n minus n minus 1, 0 to infinity, 1 plus r square minus s r is power of n minus 1 dr, and this is the polar coordinates. So this integral is the right hand side. Integral is convergent and only if my integral 1 to infinity r is for 2 minus s r n minus 1 ds dr is convergent. So like it has no singularity at r equal to 0. So 0 to 1 integral is always exists. So to show the existence of that integral, I have to just check the integration from 1 to infinity, and that integration has same as that integrand. It has the same convergence properties of this integral. So this is equal to this 1 to infinity r raised to power of minus 2s plus n minus 1 dr, which is convergent if and only if my 2s plus n minus 1 has to be less than minus 1. So once that's the case, and this holds if and only my s is greater than n by 2. But that is what we have just assumed in our question. So thus I Rn 1 plus mod I square minus s d psi power half is finite. So since this thing is finite, so therefore we have therefore we have एक second. Therefore we have so therefore we have mod ux less than equal to the HSRN norm times I1, which is a constant, holds for all x in Rn. And what this basically implies, the L infinity norm of this thing has to be less than some I times UHS Rn. And that holds for all u in my DRN. So this holds for my all DRN. Now, once that's the case, now let U to be in HSRN. Then by density, there exists a sequence UN in DRN such that UN converges to U in HSRN. So once we have this density, we have the sequence, and what this basically gives us that this sequence is actually UN minus UM L infinity Rn, so has to be less than some constant time UN minus UM this Rn. It is actually a Cauchy sequence in L infinity norm, and then with help of this Arzela Pauli, we eventually actually get this convergence in the L infinity norm. And once that is there, since these are sequences, so the limiting sequence will again a content sequence, and so by Arzela Pauli, we have a result. So next, what we would like to see is that there's some of the properties of these HS fractions of the spaces, that how these are embedded into each other. So the next embedding, which like which we some more or less is in the same nature. Uh, so again, but we have seen this embedding, but we can prove in a Fourier transform way as well. So for S1 less than S2 infinity, prove that HS2 Rn to be a subset of HS1 Rn. Solution. So again, we use the same characterization of HS_Rn, which is nothing but all those functions in L2Rn such that 1 plus mod xi square whole is power of S by 2 into U hat has to be L2Rn. So that's what we have to prove. So what we start with that U to be in HS2Rn. We will eventually show that this is in eventually in HS1Rn. So to show this, we considered the integration of Rn of 1 plus mod xi square whole is power of S mod U hat into uh, this S2 actually. So no, we have to show it to be S1. So this is S1. So we have to show that it lies in HS1. So this is we have, and this actually can be written as integration of Rn of 1 plus mod xi square of S2 by 2 U hat xi whole square And then we have 1 plus mod xi square, or square s1 minus s2, whole divided by 2 into 2 d xi. And if you note that this 1 upon, this is nothing but as s2 is greater than s1. So we have this thing is less than or equal to Rn integration of 1 plus mod xi square whole is power of s2 by 2 u hat xi in the whole square dz, but this is nothing but the hs2Rn, the square of this norm. And once that is there, we have just 1 plus xi square s1 by 2 suppose u hat square belongs to L2Rn, and once that is there, this will imply that u has to be h of s and Rn. So next, once this embedding is there, what we try to do, we have this one more containment. We have one more inequality. So that is known as the interpolation inequality. We have this sort of inequality for the LP spaces, but same can we have for the Sobolev spaces as well. So this is the next question. So again, if it let n to be less than s2 and s to be theta s1 plus 1 minus theta s2, and theta belongs to 0, 1. If u belongs to hs2 Rn, then u of hsRn has to be less than or equal to the u of hs2Rn uh, 1 minus theta, and u of hs1Rn is to power of theta. So this is the inequality which we wanted to prove. So by the previous question, we have u belonging to h of hsRn and u belong to h of s1Rn, provided u belongs to h of s2Rn. So this we know from our previous result that once it's in one Sobolev space, it has to lie in the lowest Sobolev space as well. Now, integration of Rn 1 plus mod xi square whole is power s. You had psi mod square d xi is equal to integration of Rn, and this thing now can be done as this. Yes, I know is nothing but theta s1 plus 1 minus theta s2, and this is u hat xi 2 theta plus price of 1 minus theta d xi. So I can write this as this thing. And but well, we have here, we have 1 plus mod xi square times theta times S1 into U hat psi times 2 theta. This belongs to L of 1 by theta Rn and 1 plus psi square mod xi square 1 minus theta S2 into U hat psi twice of 1 minus theta. This will belongs to L of 1 upon 1 minus theta Rn. So this again holds. Moreover, 1 upon 1 by theta plus 1 upon 1 minus theta is nothing but theta plus 1 minus theta, which is 1. So 1 by theta and 1 upon 1 by theta are conjugate exponents. Applying applying Elder inequality, we get integration of Rn of 1 plus mod xi square is per s into U hat xi whole square d xi has to be less than equal to the integration of Rn of 1 plus mod xi square s2 into mod of U hat psi square d xi or square of theta. So 1 upon 1 over theta is just theta only into integration of Rn of 1 plus mod xi square what is for so I believe one is S1 and this has to be S2 mod of U hat psi square d psi into 1 minus theta. So what this eventually this implies that the HS norm of Rn is nothing but less than equal to the H S1 Rn norm into theta into U of H of S2 Rn of 1 minus theta and that holds for. So this is the inequality which we want. Next we have another question. Now we would like to use this compact embeddings which we have learned, and what we will have this. We can show that the best constant in our Poincare inequality is actually achieved. So number 4, best constant Poincare inequality. So let omega be a subset of Rn be a bounded domain. Then for any u in W1P of omega, we have integration of u mod u raised power of p omega has to be less than equal to some constant time, the integration of omega of the p of the gradient. So we have to show that prove that the best constant in star is achieved. So how do we show that the best constant in the this point inequality is achieved? So to prove this, what we do, we actually try to convert this best constant problem into a minimization problem. So that is actually the way how we actually define the best constant. And so let C be the infimum of omega, gradient of phi raised for p, such that my phi belongs to W naught 1 p omega, and my integration omega of phi raised for p is 1 only. So how do we basically prove that there's such lambda one? So there is some function says that this thing holds. So what we try to do, we assume S to be equals all those fine h naught 1 omega, such that my integration of pi square over omega is equal to 1. So then this c is nothing but the infimum of my this for p, sorry. So we know that we're Poincare. This S is we have C to be strictly positive. So we have this thing because this is always has to be greater than equal to the uh the the p norm. Moreover, if we take some minimizing sequence phi n, then the phi n, and we have this. Oh, sorry, we have just one more. So this is W naught 1 p omega. W naught 1 p omega. This converges to some constant c. This will converge to a constant c, which is the minimizing minimum value. It's all is for p as well. Also, the phi n has LP norm. Omega has to be equal to 1 only for all n in n. Just what do we have here? We have here is this phi n is bounded in W naught 1p omega this by Rayleigh's compactness theorem since omega is bounded. So we are assuming this omega to be a bounded domain. We know that they exist subsequence phi n k such that we know that phi n k converges weakly to psi naught in h naught 1 omega sorry in W naught 1p omega, but this bidirect compactness will imply this phi in k is converges strongly to phi naught in LP omega. So here we're basically using the from the boundedness we have a weakly convergent subsequence, and then from the Rayleigh compactness we have this sequence to be convergent in LP in a strong sense. Thus the limit of k tending to infinity of integration of omega of mod of phi n k whole is for p has to be equal to this thing. And this whole are one only, so this implies this integration of phi naught p is 1, and thus phi naught belongs to my unit sphere, basically where it has LP norm equal to 1. Moreover, we have this since convergence weakly, phi n k for convergence weakly to phi naught. We have by the so this is something we can prove the lower semi-continuity of the norm. We have this integration of omega of phi naught. So grad phi naught is for p has to be less than equal to the limit for sk tending to infinity of omega grad of phi in k or is for p, which is nothing but this is nothing but less is equal to c only. So this is since pi and k is a minimizing sequence, but what do I know about this phi naught? This phi naught belongs to S. What this implies, this c has to be less than equal to integration of omega of grad of phi naught is for p, because now phi naught is a member of S, and we have infimum of on this unit sphere. So we conclude that the integration of omega of grad of phi naught p has to be equal to c. When that is equal to c, we have basically thus we have our best constant to be achieved. So next, once we have proved this best constant of Poincare inequality is achieved, let's have one more version of Poincare inequality. So the Poincare inequality which we did is for the Sobolev functions, which are actually a particular space of Sobolev functions, which is W naught 1p. So we can have a new modified version of Poincare inequality for all the functions in the Sobolev space in the space W1p. So we can have that particular version of Sobolev Poincare inequality for this whole space. So clearly that not holds. So the problem with have the poincarity to hold for all the functions in W1P is that if you take a constant function that has some positive LP norm, but if I take the grad norm, it has sort of zero, and I cannot have any constant has which holds for these constants. So to deal with that, we have this newer version of one inequality which deals with the constants. So the idea is to actually consider the LP norm with the difference of the average integral. So what exactly I mean by that? So let me write this thing to you precisely. So let Q be a bounded connected open subset of Rn with the C1 boundary. Assume that P is 1 to infinity, then they exist. Then show that they exist a constant C, which depending only on N, P, and U, such that the norm of U minus U LP U has to be less than equal to some constant times du of LP U for each U in W1P U, and UU means the integration of the measure of U and integration over U of U dy. So this is actually also written as integral with the bar, like with the dash sign U dy. So the proof actually uses this compactness theorem, the rich compactness theorem. So let us try to do this. So we actually argue by contradiction. Let's denote this by 1, assuming 1 doesn't hold, then for each k in n natural number, there exists a function uk in W1PU satisfying this uk minus the uk average u of LPU has to be greater than some k times d of uk LPU. Let's name this to be u. Once we have this, because I take the constant to be k, and we doesn't have this, so we have a function user which doesn't satisfy the inside for this constant. So now take Vn Vk to be define Vk to be by Uk minus this UKU whole divided by UK minus UKU of LPU. So then since this is strictly greater than, so this norm has to be non-zero from 2. So I can divide it by this thing. And this is I'm doing for all k and then if I take the average integral of VKs over U, this is 0. And this VK will have the LP norm of U again turns out to be 1. We can again prove. So this is a direct computation. Moreover, to imply that the D of VK norm LPU now has to be less than equal to 1 by K for all K in, and this is another estimate. So let's name the estimate to be 4. Thus, we have this dvk to be this vk sequence to be bounded in W1P U. Thus, by Rayleigh compactness theorem, there exists subsequence Vkj j1 to infinity of Vk and a function V in LPU such that Vkj converges strongly to V in LPU. So this from the compactness theorem we have. Moreover, we have this average integral of V to be 0 and the LP norm to be 1. So this again comes from the compactness. So and the VKs have LP norm to be 1. So the norm converges. We have this, and again the average integral is 0. So this is again a byproduct of my compactness and the strong convergence of VKJ to V in LP. So we can use this like the DCT. We have this. But let's name this thing to be 5 and this to be 6. But in view of 4, we have for each I in 1 to n and phi in Cc infinity of omega, sorry, Cc infinity of u, that integration of u of v phi xi dx. So this is nothing but the limit of kj tending to infinity of u vkj phi x xi dx. This is nothing but minus limit kj tending to infinity. So these vkjs are in W1P. So these are actually u vkj, and then we have integration with respect to xi of phi dx. But what do we know? That these derivatives are less than or equal to 1 by k, the norm less than 1 by k, and so the limit has to be equal to 0. Plus, we have v to be in w1pu with dv to be identically equal to 0 almost everywhere. But what this implies, we have seen the last tutorial session that when that is the case, this will imply that v has to be constant almost everywhere. But we have the average integral of u to be 0. That implies that v has to be identically equal to 0 almost everywhere. But this will imply that the LP norm of this has to be equal to 0. But we have the LP norm of v to be 1. So we have a contradiction. We have a contradiction, and thus we have a result. So this once we have a result, so this is a modified version of the Poincare inequality. We just have to eliminate the average integral. So we that will actually consider the cases when we have u to be constant. So constant will have the average integral to be same itself. So constant minus constant will give the value 0. So then that deals with the case of the constant, and we have this inequality for the all w and p functions. So next we have a better estimate when we have a domain to be a ball. So the Poincare inequality for a ball will give some good estimates. So this next question is based on a Poincare inequality, but with the inequality to hold on the ball itself. So question 6 section, I think what the Poincare inequality for a ball. Okay, so we can prove the Poincare inequality for the ball. Assume 1 less than p less than equal to infinity. Then there exists a constant c depending only on n and p, such that u minus the u xr. So what is xr? Is again the average integral over the ball. LP of bxr less than equal to some constant time r times c du of LP bxr. For each ball bxr subset of Rn, and each function un w1p v0 xr. So we have extra R in the right hand side, and that helps like have a better estimate when basically my ball having a size small. So these are sometimes helpful when we are estimating some inequalities. So the case, how to prove the case? First, we consider the case u equal to b 0 1. So this is the unit ball from previous question. We have a result. So why we have a result? Because the R is equal to 1 only. So we don't really have to consider bother with the case. So now let us consider the general case. General case. So U will belong to W 1P B naught X comma R. So what we try to do, we try to convert our problem back to the unit ball. So for that, we consider Vy equal to U of X plus Ry, and Y belongs to my unit ball. So once Y belongs to unit ball, we have this U is in the unit in the ball with center X and radius R only. Then we will in the W1P P naught 0 1, and we have V minus, so we can apply the point current quality for the unit ball. V minus V 0 1 LP V 0 1 less than equal to some C times dV of LP V 0 1. So let us try to see what are the both my left and right hand side are. V minus V of 0 1 LP V 0 1 list for whole list for B is nothing but the integration of V 0 1 Vy minus the average integral V 0 1. This V 0 1, let us evaluate this thing first. So this is nothing but the average of the measure of the unit ball V 0 1, integration of V 0 1 V by dy, and this is nothing but the measure of my unit ball into V 0 1. And what is Vy? Vy is nothing but u of x plus ry dy. So let us try to change the variables. So we take x plus ry equal to z. Then r s power of n dy will be equal to dz. And we have the integration of the measure of 0 1 times. So when my r varies in v 0 1, my z varies in v 0 r. So this is vx r uz and r s power of n. So it will be dz r s power of n. So this whole thing is nothing but the measure of v of 0 r, since r power n will v can be written as this thing, and this vxr. And we didn't know that the big measure is translation invariant. This is nothing but integration of bzr, sorry, bxr, integration of bxr uz dz. So this is nothing but the u of at x comma r only. Thus, integration of v01 by minus v01 is nothing but integration of v01 u of x plus ry minus u of xr dy. And again, we transform x plus ry to be some z only. So this is nothing but b of xr u of z minus u of x comma r into dz whole divided by r is power of n. So this will be the right hand side. So left hand side, sorry. And finally, we have to consider the dv of LP B01 whole square of P. What will be? This will be integration of B01 of d of V mod risk for P dy. What is my so what is my V? V is Vy is U of x plus ry. What this implies that dv of phi is nothing but du of x plus ry dot so this will be the modulus will be equal to mod of dvy mod of times r which will less than equal to less than equal to the r times this thing, and eventually we have this thing v01 d of u du at x plus ry or is power of p into r is power of p dy, and then we again change a variable x plus ry to z. This will give me v of xr du of z what is power of p r is power of p dz into r is power of n. So thus finally we have u minus u of xr lp of vxr to be less than equal to some c times r times du of lp of vxr. So this comes from the fact that r and r will cancel from both inside, and taking the 1 by p power on both inside, we ultimately end up having a multiple of r in the right hand side. Okay, so that's we have the point carrying quantity for the bond.